Yes. Yes.
Okay, so this is where we are. So we have modules 1 through 4, and then we go to these transition topics, and then we are in the decision analysis, and this would be the last topic we would cover in decision analysis. So multi-attribute decision making. So let's start with few examples of decisions that we face in real life, right? So let's say you're trying to buy a personal computer. Of course, we have different preferences, and some people would say, I want the cheap computer that does what I need to do. Another person might come back and say, no, you want the latest and the greatest, right? So if you all you care about the money, if all you care about was money, what would you do? Most likely you would say, I buy the cheapest computer, or maybe not buy one at all. In fact, there are some people who would just go to the library and use the computer there or at the university. They don't have to buy a computer. And this is a point I often make, that when many times we think that we do have a decision and we have to act, sometimes not acting is also a decision. Okay. So on the other hand, if you all you care about is performance, what would you do? In this case, you would say you buy the most high-end computer, which usually costs a lot of money. But you generally care about both. And this is true for pretty much everybody. I mean, I can talk about my parents who are not necessarily computer savvy, but then even they realize after a while that the computers they have won't even open websites, or they can't even check their email. On the other hand, there is almost no upper limit to how much you can spend on computers. So at some point, you would say, you know what, the incremental benefit I'm getting out of this is not worth the money I'm spending. So we simultaneously care about both, and we have trade-offs between these two attributes of cost and performance. We can dig deeper and talk about, performance is not just one monolithic thing out of a system. It's composed of many sub-attributes as well, in which case, of course, your analysis gets more involved, but the general idea is that you're simultaneously caring about multiple things. We've already worked on the design of a chemical scrubber. Okay, we went through the process. Again, if we only cared about performance, we'll use the most expensive parts and probably over-design it. And this can be shown using expected utilities too. So if we, let's say, had we haven't talked about multi-attribute utilities yet, but if we set up our problem so that performance is valued, we play through the design optimization process, and we'll end up with something that values performance over cost, and it'll be something that's often over-designed. Again, if we care about only cost, we'll use the cheapest parts. We generally care about both, right? So what is the good trade-off? And that's pretty much where design lives. Design is just, I mean, you can think of design process as managing trade-offs sometimes. Okay, so buying a car is a multi-attribute problem as well. You think about fuel economy, acceleration, color, price, and so on and so forth. In fact, I would even say that one project we worked on, which involved multi-attribute decision making involving car buying decisions. This was data involving about 19 attributes, and it starts challenging a lot of the decision making methods we have. So we have many, many attributes going on. Here's just some examples of what attributes we typically think of. If you are working for a company, you deal with suppliers quite a bit, right? So most car companies these days are assemblers. They don't build pretty much anything. So some companies will still build engines, but they buy seats from this company. They buy fasteners from that company. Their sheet metal comes from over there. Their window regulators come from over there. Their injectors are made by Bosch or whoever. So they assemble things, and then all those parts have to arrive on time. They have to be reliable. They have to match the specifications, and so on and so forth. So if you're selecting a supply, you'd say, okay, well, reliable. Is your parts reliable? Are you timely? Do you give it at a realistic price? Is the quality good? Timeliness? Do you provide things or parts to us when they're needed? So, and then we can extend this to a little bit more engineering examples. We can again if in fact, one of the things that we see in aerospace quite a bit is minimize cost, right? Let's say a simple structure within a larger, let's say, system. If the explicit objective is to minimize cost, what would you do? Okay, well, maybe you'll use alloys that are cheap. Maybe you'll use smaller dimensions, so on and so forth, right? What if you said, I want to minimize deflection? So now suddenly you're thinking performance, and then you would say, okay, well, I would maybe make it of a more sturdier material, more rigid material. I can use more material, make bigger beams, larger cross section, and so on and so forth. Or maybe even look at more complex designs. Maybe I can do more expensive analysis to make sure that it doesn't deflect. Okay, we can reduce the weight, and then you will have different types of decisions you would make. Your cost and transportation will go up if it's heavy, because obviously the material costs more, and then transporting and installing it costs more. Maybe you'll have to pay more to transport it. Maybe you'll have to the installation process is more involved. You need bigger equipment, so on and so forth. So decisions rarely involve single attributes. That goes without saying. I can't think of a single decision situation where only one attribute is involved. Especially if we look at the entire decision and not just like look at a small snapshot or a small region of the feasible space. We have, for example, if we say, okay, well, all things are figured out, now we just want to reduce cost. Okay, you can talk about it in certain small universe, but in general, almost all decisions will involve multiple attributes. And decision making requires finding the best trade-off between competing attributes. So they compete with each other. If attributes simultaneously improved, life would be set. They don't. When you make things strong, they start costing money. They start becoming difficult to, let's say, transport. When generally performance in a product, whether it's a car or a computer, improves only at the expense of cost. So the questions that we would like to answer is, how much should I pay extra for a design that simultaneously reduces weight by 10% and increases reliability by 30%? So three things are happening. There's cost as an attribute, there's the weight of the part as an attribute, and also reliability of the part as an attribute. And they're simultaneously changing. How much extra in money for this much reduction in weight, for this much increase in reliability? And once we think like that, we start wondering, we have a lot of things that we need to add to our basic model we had in the last lecture on single attribute decision making. We need to know the trade-off behavior of the decision maker, in addition to their preference order for each attribute, in addition to their attitude toward risk, right? So risk is not just over one attribute. Now you have risk attitudes general over multiple attributes. You need to know how much of one compensates for the other. So the problems got really difficult very quickly, but nothing really to worry about because we have the framework. The 5 axioms we learned are perfectly applicable to multi-attribute decision-making problems. The idea of utility function still holds. So let's see. Axioms hold. Decision analysis is axiomatic. If you went back to the axioms, you have all the tools, all the basic tools, I should say, necessary available to you to solve multi-attribute decision problems. So we still deal with utility functions, and they are a crucial tool in engineering decision analysis. So we usually would write u of x1, x2, x3, and so on and so forth. So let's say if you have n attributes, your utility function is a sum total of those attributes. And you can start thinking that the interplay has to be captured in this utility function, right? So another good news is that the value of lottery questions is still there. Okay, so for single attribute cases, when we had intermediate options on the left-hand side, and best on the top here, worst in here, and then we ask the decision maker to provide the value of P here. That still holds. So the only generalization we do is that as opposed to saying best on the attribute, we say best on all attributes. And here we say worst on all attributes. Now, this is not globally worst on all attributes. This is just in the ranges of negotiability. So for each attribute, you'll have range of negotiability, least and best, or worst and worst best levels. Here we have what we will assign the worst outcomes for all attributes, your best outcomes for all attributes, and then the intermediate values for some of the attributes. So right away, we see that if these are intermediate, even for one attribute, it could be multiple, then this outcome on the left-hand side, the sure outcome on the left-hand side, is not as preferable as the best on all attributes option, but is more preferable than the worst on all attributes option. So then it's just a trivial matter of some definitions. We say, okay, multi-attribute utility value of 1 means that all attributes have met their best possible level simultaneously. And a multi-attribute utility value of 0 means that all attributes have met their worst possible level simultaneously. So just one simple generalization and a definition, and then we're good to go. Now, obviously, this means best level in the range of negotiability, not best global. So in the range of negotiability that you've defined, they have hit the best level here. And then we assign that the utility of 1, we assign this to the utility of 0, and then all other options which will live in that, so to speak, hypercube will have a utility between 0 and 1. Right, so the next thing we talk about is trade-offs, and we will spend some time thinking about how attributes trade off with each other. So, of course, we work with many notional examples. So here the example is fuel economy and cost in a vehicle. Now, I work in Michigan, so pardon me if a lot of my examples include automobiles. There's a lot of automobile industry in Michigan. So either way, so we have two attributes, cost and MPG. On the x-axis, we have miles per gallon. Now, by convention, we make sure that the utopia point is at the origin, which is saying that the best things happen here. So since people prefer more miles per gallon to less miles per gallon, we say that we put a negative sign in front of it so that the maximum value happens here. And cost, already people want to minimize, so the minimum value happens here, and then this becomes the utopia point, which makes this the nadir point, the point where all attributes are at the worst possible level simultaneously. In this case, we only have two attributes, so it's easy to see it visually, but the same concept can be extended to a larger number of dimensions. Of course, things become difficult both from interpreting or interpretation standpoint, but also the mathematical models that will model that kind of trade-off behavior. So we have what we call indifference curves. So let's say if we have a curve here, this one, this is saying that as you move from left to right, or left to right, or right to left on this curve, cost and MPG are constantly changing. But the change in one attribute is just enough to compensate for the change in the other attribute. It means one gets worse and the other gets better at precisely the rate that you stay indifferent. So we call them indifference curves. So here we have a few examples of indifference curves. Of course, they're all over the place. We drew some discrete examples. So here we have, let's say, on this curve, we have 3 options we can look at. And then they say that these 3, the decision maker is indifferent between. And on a different curve, we can say the same thing, the stars. So the decision maker is indifferent between this star, and this star. They don't care because, for example, this one has a certain miles per gallon. This one is better in miles per gallon, but also costs more. This one is even better in miles per gallon, but costs even more. So the offset is there. And then each decision maker will have their own difference curves. So they will have different slopes. They may have different curvatures and so on and so forth, right? So that captures your trade-off behavior. So somebody might say that I would give up much more in the miles per gallon category for reduction in cost. Somebody else might say, no, I'm a green customer. I want my car to have very high miles per gallon, and I'm willing to pay more. So those kinds of things can be captured in indifference curves. Of course, difference in different curves will have different utility values associated with them, different desirability, and the typical idea is that as you move towards the utopia point, the utility value is increasing, and then these curves will have high utility. So this curve, which has stars on it, corresponds to a higher utility value than this curve that has circles on it. Now, from an assessment standpoint, it is also seen that people find it much easier to provide indifference curves. So, and I do this in my class all the time. I will give examples of any two attributes, and I'll ask students to provide indifference curves, and they start with, let's say, 1 point here. They play with the numbers a little bit, and they get another point, and they get another point, and then slowly they start getting the idea, and then they're able to draw indifference curves, which can be one way of assessing multi-attribute utility functions if you use indifference curves. Okay. Okay. So now we'll go to the next concept, which is a lot of things are pretty self-evident when you start drawing utility indifference curves. For example, let's say we start with a reference option, which is this circle in the middle. And then we draw these two lines, which basically separates this space into quadrants. It's easy to see that any option here is worse than the reference option. That goes without saying, because you could, if you move from this point to anywhere in this quadrant, you have simultaneously worsened both attributes. Even if you moved just straight up, you didn't change y1, but you did change y2, and you made it worse. So any option in this quadrant is strictly worse. Any option here is strictly better because you made improved at least one attribute, or you improved both attributes simultaneously. And that's something that is used in multi-attribute optimization problems, multi-objective optimization problems, especially if we use, let's say, multi-objective genetic algorithms, that we actually do this multi-attribute sorting or some other technique which makes this direct comparison, and we can, without even knowing much beyond the preference order for these attributes, we can accept and reject solutions. The real challenge comes when, starting with this reference options, you have to compare something in this quadrant or this quadrant, because anything in this quadrant is improving one attribute but worsening the other. So the idea there is that now it depends on the decision maker's specific attitude towards a trade-off. So somebody with this curve will say, I have a different trade-off rate between y1 and y2. And for example, when I go from here to here, y1 value going from here to here, I have a certain decrease in y2 that compensates for it. For a different decision maker, for the same change, a less change in y2 compensates for it. So these kinds of things is what differentiates the decision maker, and then their decisions can be drastically different. So somebody who prefers a faster car and is willing to pay more, or higher miles per gallon, willing to pay more, or higher performance, they will have different curves, they'll make different decisions, and then manufacturers will often target different market segments differently, and so on and so forth, as opposed to just making one product. And then the other side of this is, what does nature allow, right? So if you just looked at what we saw in the last slide, you would say, okay, well, yeah, why don't we just always go for something that's here? Okay, and we can do this, and this reference option is not set in stone. We don't have to start with this middle. We can be anywhere, and then we can draw 4 lines and say anything here is better than that reference option. Anything to the bottom and left of that reference option is better. But that's something that's just a matter of choice. This is just preferences. Okay, so we'll keep that in mind. This is just preferences. The other thing that I want to reiterate, and I'll reiterate quite a bit here, is that 2 attributes is, again, would be considered a simple decision problem. Typically, number of attributes is larger. And when you have a large number of attributes, these visual methods start failing. So we really cannot, I mean, maybe 3 attributes, we can have, we can get trade-off curves and so on and so forth. But beyond that, it just becomes hard to draw, hard to analyze, how to assess, and then they become more of a hindrance. So that's why we go to the multilinear utility functions and things like that, which we will cover later in the class. So great. So one thing to keep keeping in mind is that this problem gets much harder when you have many more attributes present and not just 2. And the other thing to keep in mind is that people make different decisions based on their preference curves, and they may prefer something here. That's just preferences. It's not what nature allows. So let's go and see what the nature allows. So we have the same 2 attributes, y1 and y2, and we start with the reference option. And then we draw 2 lines like this. If we find a solution that's here, of course, that's definitely worse. Any solution that's here, that's definitely better. This is the information that we have from the decision maker. They prefer less of these 2 attributes. And in this region, we can't say, well, we don't know. We don't know your preference. Okay, and that's okay. So a lot of multi-objective optimizers, which we referred to many times in this class, can work just from this information and give you a useful set of solutions, which we will see in a minute. So something here is rejected, something here is accepted, and that becomes the reference option. So once we find something like this, there's no point keeping the old point. We take the new point. And then we get a collection of these points like this that are in each other's can't say region. I can't say if this is better because you see this belongs in that quadrant of this point, and then this belongs in that quadrant of this point, and so on and so forth. So dominance, multi-attribute dominance does not exist between these attributes or these options. And what we end up with is what's called the Pareto front. Okay, so Pareto front shows unavoidable trade-offs in a decision. These trade-offs cannot be avoided. In other words, nature does not allow you to simultaneously improve any of these attributes associated with any of these outcomes. So if you take this design, this outcome, nature does not allow you to simultaneously improve y1 and y2 beyond that. Nature will allow you to improve y1 by moving left, but you will by definition have to also go up and improve y and worsen y2. So if we go from here to here, we are improving y1, but we're worsening y2. We go from here to here, we're worsening y1, we're improving y2, and that's why it's called unavoidable trade-offs. So there's a few caveats here. Of course, this extends to any number of dimensions. It just becomes harder for the optimizer to come up with those, but 4 or 5 attributes are pretty manageable. This doesn't have to be discrete. Pareto fronts can be a continuous set of solutions. You know, you have, let's say, a continuous variable, you change and you're at different points in the Pareto front. And no improvements are possible. I already said that. And this is something that you can present as a precursor to a decision. So there's two approaches in decision analysis that we can talk about. One is that we assess utility functions, and then we use that intrinsically in a part of like an optimization problem where we make utility function the objective, and you can find the solution that maximizes the utility. Okay, that's one approach. The challenge with that approach is that sometimes we don't have an accurate utility function, sometimes we don't have it at all. With this approach, just knowing that what the good solutions are, we can first converge to this set of solutions and then either hand them directly to the decision makers and have them select one of these solutions, or we can use the utility function to select the best point on these solutions. And just having these solutions that are available, feasible, and realizable using the design within the design constraints is a good thing to have to frame our decision problems. So Pareto fronts are a very powerful tool that's either used quite a bit in engineering decision making in organizations where people want to present the best multi-attribute solutions so that the next level manager or decision maker can select from that. Okay, so now there is, with that understanding of trade-offs and multi-attribute trade-offs and indifference points and so on and so forth, we now can now talk about different ways we can assess and construct multi-attribute utility functions. For the most part, the approach will remain the same between single and multi-attribute utility functions. It's just you have to always carry all these different attributes with you in your assessment process. So there's two commonly seen approaches that we see in the literature. Both of them are sound in some ways, and they both have their limitations. So one is what's called the value function approach, which is you first model the trade-offs between the attributes, whether you do it through indifference points or you do other types of assessments, and then you fit a single attribute utility on top of that, right? So value function combines all these attributes into one value function, and then you find a single attribute utility function over that value function. The multilinear utility function approach, which relies on certain independence conditions, which will take single attribute utility functions. So you can individually assess single attribute utility functions associated with all of your attributes, and which is something that you already know using any of the assessment procedures, and then you can combine them using the multilinear function. Now that is one of the I would say one of the better techniques in terms of applicability. I've used it quite a bit in my research, and I think that it's easy to construct. It's intuitive and it works, except that it depends on those independence conditions, which we will talk about later in the lectures. So the three conditions we will talk about are preferential, utility, and additive independence conditions. And those are the ones, at least the first two are the ones that allow you to use more certain types of utility functions that are easier to assess and use. And I think that that's where we can end, because I think we have covered the other topics separately.